The Poisson distribution is a fascinating tool for understanding random events. Imagine a store where, on average, 5 customers stroll in every hour. What are the chances that exactly 3 will show up in a random hour? By applying the Poisson formula, we find that this probability is around 14%. Now, consider a factory where machines break down, on average, 2 times a week. If we want to know the likelihood of exactly 4 breakdowns in a week, we again turn to the Poisson distribution. After calculations, we discover that the probability is approximately 9%. This distribution helps us make sense of the unpredictable, whether it's customer arrivals or machine failures, providing clarity in the chaos of randomness. Welcome back. Let's dive into the Poisson distribution, another widely used discrete probability distribution. This distribution is perfect for modeling the number of times an event occurs within a fixed interval, such as time, distance, area, or volume. The Poisson distribution is often used in fields like operations, logistics, and healthcare to analyze random occurrences that happen independently of one another. The Poisson distribution describes the probability of a given number of events happening in a fixed interval, assuming the events occur independently of each other and at a constant average rate. The probability of observing exactly k events is calculated using the formula. The probability of k events is given by the product of the average rate, denoted as lambda raised to the power of k, multiplied by e raised to the power of negative lambda, divided by the factorial of k. Here, lambda represents the average number of events in the interval, k represents the exact number of events we are calculating the probability for, and e is a mathematical constant approximately equal to 2.718. Let's consider a store where an average of 5 customers arrive every hour. What is the probability that exactly 3 customers will arrive in a randomly selected hour? Define the variables. The average rate, lambda, is 5 customers per hour. The number of events, k, is 3 customers. Step 1. Write the formula. The probability of exactly 3 customers is calculated as lambda raised to the power of k, multiplied by e raised to the power of negative lambda, divided by the factorial of k. Step 2. Calculate each component. Lambda raised to the power of k is 5 raised to the power of 3, which equals 125. E raised to the power of negative lambda is e raised to the power of negative 5, which is approximately 0.00674. The factorial of k, which is 3 factorial, equals 3 times 2 times 1, which is 6. Step 3. Combine the values. Multiply 125 by 0.00674, which equals 0.8425. Now divide 0.8425 by 6, which equals 0.1404. Final answer. The probability that exactly 3 customers arrive in a randomly selected hour is approximately 14%. Here's another example. A factory machine breaks down an average of 2 times per week. What is the probability that the machine will break down exactly 4 times in a given week? Define the variables. The average rate, lambda, is 2 breakdowns per week. The number of events, k, is 4 breakdowns. Step 1. Write the formula. The probability of exactly 4 breakdowns is calculated as lambda raised to the power of k, multiplied by e raised to the power of negative lambda, divided by the factorial of k. Step 2. Calculate each component. Lambda raised to the power of k is 2 raised to the power of 4, which equals 16. E raised to the power of negative lambda is e raised to the power of negative 2, which is approximately 0.1353. The factorial of k, which is 4 factorial, equals 4 times 3 times 2 times 1, which is 24. Step 3. Combine the values. Multiply 16 by 0.1353, which equals 2.1648. Now divide 2.1648 by 24, which equals 0.0902. Final answer. The probability that the machine breaks down exactly 4 times in a week is approximately 9%.